Hello and welcome back to Algorithmic Game Theory. I'm excited that we're starting a new topic today, which is mechanism design. More precisely, we're first starting with mechanism design with money, before later this semester we'll also come to mechanism design without money. So far, our goal was just to understand games and strategic behavior happening in games. Today, we're now asking the question, how should we set the rules of the game to achieve some desired outcome? And not only today we're asking this question, but effectively for the remainder of the semester we're kind of asking this question. And as an introductory example, I'd like to consider the question of selling a single item today. So we might now have one item that we might want to sell. Our goal is now to make just the world as happy as possible. So our goal is not to make as much money as possible, but just to make sure that the value that the world is getting out of this item, which is valueless for us, is the highest possible. What might this look like? One thing you might want to do is you might want to run a first price auction. What could that look like? Well, you have a bunch of bidders. Each of them writes down their bid, how much they are willing to pay for this item. And then you figure out who bid most. And in this case, the highest bid was 20, so we sell the item for 20 euros. Is this a good idea to sell an item like this, or are there better ways? Well, to discuss this question, we first have to derive a mathematical model, and we first have to kind of capture the probably strategic behavior happening in here. What we're seeing here was a so-called sealed bid first price auction. We have, again, n players, or as we also call them in this context, often bidders. And each of the bidders now reports one bid. They all do this at the same time. And then the bidder with the highest bid wins and pays his or her bid. Of course, we might want to define a tie-breaking rule here, because there might be identical bids, in which case we might want to now say, okay, the bidder with the smallest index, for example, wins, or whatever other tie-breaking rule you prefer. How do we now capture the agent's preferences? So what do these agents, bidders, players, however you want to call those are just identical. Those things just mean all the same here. How do we express this? Well, what we do is we assume that each of the bidders has a value for winning. And this is a non-negative real number. So bidder I has value VI for winning. VI is some non-negative real. And what will then the utility be? Of course, bidder I, if he or she wins, he or she has to pay his or her bid. So the utility of bidder I given bids B will be VI minus BI if bidder I wins with bids B, and it will be 0 otherwise. So this VI is just in terms of units of money expressing how much do I value the item. And what we now say is, okay, my value, my utility is my value minus what I'm paying, and what I'm paying in this case is just my own bid. If I win. If I lose, then my utility will be 0 because I'm going home with as much as I came with. Now, if I'm bidding, for example, more than my value and I'm winning, then I'll have negative utility because I'm paying more than my actual value for the item. But hopefully I'm actually bidding no more than my actual value, and then I'm seeing some utility here. Is this a good game or not? Maybe. Well, it's at least for one advantage is that it's really easy to explain. But what is a disadvantage? Well, we don't actually know. Nobody knows these values in advance, so we don't know either. That's really important. Nobody knows these values in advance. But you better actually know what the other bidders are bidding to now choose your best response. And let's see this once again in our example. These are the bids in our example. And now let's ask, is this a pure Nash equilibrium? Is it a pure Nash equilibrium for these players to bid this way? And even if we don't know their values, we see, well, this cannot be a Nash equilibrium. This cannot be a pure Nash equilibrium because how should this bidder bidding 20, how should this ever be a best response? If this bidder bid, for example, 702, then the player would definitely still win, but pay far less, and this way also have a higher utility. And the amazing thing is that there are better ways of designing such a mechanism for which there is not only a Nash equilibrium, but for which bidding is super easy. And this is called a second price auction. And this is what we will see next. So now we are moving to the second price auction. Once again, what was the first price auction? The seed bid first price auction. Each bidder reports a bid, and then the bidder with the highest bid wins, and he or she just pays his or her bid. And what we were seeing was that usually truthful bidding, for example, isn't a pure Nash equilibrium because if you're winning by a big margin, then you want to decrease your bid. Your true value, this is usually not a best response. The second price auction is a little different because it does only one thing in a different way, namely, what does the winner pay? And now the winner doesn't pay his or her bid, but the second highest bid. And this has some amazing consequences. So a sealed bid second price auction works as follows. Again, each bidder reports a bid and the bidder with the highest bid wins and pays the second highest bid. So what will the utilities be in this case? Utility of bidder I when the bids are B will be Vi minus the maximum of all j which are not equal to I, Bj, and this is if bidder I wins. And otherwise it is still 0. And somehow here bidding is much easier because by the bid you choose you cannot actually influence your own payment. How much you pay doesn't depend on your bid. So you bid some way, and this makes sure that you win or don't win, but it doesn't affect your payment. And this way, this entire term here, this is independent of BI. The only thing that matters, why BI matters, is do you bid more than anybody else? And indeed, as we will now show, here it is not only a pure Nash equilibrium to bid a true value, but even regardless of what the other bidders are doing, you always want to bid your true value. How so? Let's first define the notion of a dominant strategy. A bid BI is a weakly dominant strategy for player I with value Vi if for all Bi prime and all B minus I, the utility of bidding BI is at least the utility of bidding BI prime. And as you say, we changed notation already a little bit to indicate Okay, my utility now also depends on my value. This we will make a little formal in a second. But so here, this is bidder i's value. And we can also say that a bid profile is a dominant strategy equilibrium for valuation profile V. If for every player the bid BI is a weakly dominant strategy, and what we now claim is that in a second price auction, for each player, it is a dominant strategy to bid truthfully. By the way, this is a theorem, and all of this second price auction dates back to Vickrey from the 1960s. And you will also find the second price auction called Vickrey auction sometimes. How do we prove such a thing, and what does this even mean to prove this? We will show that in this second price auction, and let's go back to the definition of a dominant strategy, when you're bidding your true value, you will get at least as much utility as when you get bidding anything else. And this holds regardless of what the other players are bidding. So they might be bidding truthfully, but they don't have to. We don't really care. Regardless of what the other players are doing, it is always in our best interest to just bid the true value. Let's prove this. It is surprisingly simple. Let's fix some player. His or her value and the bids of the other players. Those are called B subscript minus I. What do we now have to show? We'll have to show that UI of VI, minus I, VI is at least ui of bi prime, comma b minus I, comma vi for all bi prime. We now let b max be the maximum of all utilities, of all bits except for the bit of player I. If some bit bi is smaller than b max, what will happen? Well, then the utility of bi, comma b minus I, comma vi will always be 0 because I'm not winning. And then there is the option that bi is greater than b max. Then my utility will be my value minus b max. Now, what could my value be like? My value might either be more than b max or less than b max. What will happen? If vi is less than b max, then the utility of every bit will be at most 0 for all bi. And we'll have that the utility when I bid my true value will be exactly equal to 0. So this means that the utility when bidding my true value is at least the utility that I'm getting if I'm bidding anything else. What I didn't quite mention at this point was that what happens if I bid exactly the second highest value. So if I bid exactly the maximum of the other bids, that's interesting because we don't actually care in this case. Regardless of how ties are broken, we might either also be in this case or we might also be in this case. Both is fine. And then there's now the other case that if my value is more than the maximum value, then what will my utility be? My utility will always be, let's once again check. Okay, the maximum of the two is now vi minus b max. So this is then at most vi minus b max. This holds for all bi. And at the same time, the utility of bidding my true value will be exactly equal to vi minus b max. So also in this case, we'll have that the utility when bidding the true value is at least the utility when I'm bidding anything else. And this completes our proof. Cool. So this is already our first result. For the second price auction, we see that it is actually great. It is really easy to participate in such a second price auction if you know your value, which is our assumption at this point. If you know your value, then you just bid your value, and that is about it. Then, regardless of what the other bidders are doing, you're always doing fine. And why is this true? The point is that you yourself cannot actually influence how much you're paying. All you're influencing is how much am I winning or not. And this am I winning or not, this is just determined by what the other bidders are bidding. So they are setting a threshold via their maximum bid, and then you effectively choose, am I bidding more than Bmax or less than Bmax? Bmax is what I will have to pay. And it now happens that, okay, either my value is smaller than Bmax, then I don't want to win for sure. Or my value is larger than Bmax, then I want to win. But it doesn't actually matter how much I'm bidding, as long as I'm bidding more than Bmax. And this is something we'll also understand more deeply in the following lectures. But before we get to this point, we will now first introduce a more general framework for doing such mechanism design with money. Okay, now we've seen the second price auction and also the first price auction already as two examples of mechanisms with money to allocate an item. Now we'll get to know a much more general framework of mechanisms and also how we can then Okay, so far we've seen the first price and the second price auction, and those are two examples of mechanisms. Now we'll get to know a much more general framework, out of which these single item auctions are just one special case, and we'll also see other more general cases, such as, for example, allocating multiple items. How does this now work in general? Well, we'll have, again, n players or bidders or agents. I'm using these words really interchangeably here. And this is the set n, which we will usually call 1 through n. And then we have an outcome space, which we call X. And each player, I and N, has a private valuation function, VI, mapping from X to the reals. Good. So there are multiple things we have not yet talked about here. For example, what might this outcome space be like? Let's see this in the example of a single item auction in just a second. And then what does this even mean to have the valuation function is private? This means that neither the mechanism nor the other players know this function. This was somehow explicit so far, because in a single item auction, if you knew the values of all players, if you were to design the auction, well, if you already knew the values, then you could, without any bidding, just give the item to the one who has the highest value. That is why these are assumed to be private. How would we now capture, for example, our single item auction? We might now say, okay, X should be the set of all 0, 1 vectors for which there's only one component that is 1, which means xi is equal to 1 if and only if player I gets the item. And then we'll say, okay, vi of some x will be equal to vi if xi is equal to 1 and 0 if xi is equal to 0. This is a little strange the first time you might see this, because of course, at this point, we might also choose a different outcome space. So for example, we might also just say, okay, the outcome is one integer from 1 to n, so one of the players is getting the item. This way of writing things may look a little contrived at this point, but this is how we will think about this next time. That will have a 0, 1 vector. Regardless of how you now define this, we'll now say, in this case, xi is equal to 1 if player I gets the item. And now the valuation function, once again, it maps from outcomes to reals. This will be my value for the item, which I incidentally also call vi here, as well as the function, because they kind of express the same thing anyway. Although in terms of syntax, they are actually something different. This is a real number. This is a function. And we say, okay, the value of the function is my value for the item if I'm getting the item, and otherwise it is 0. Okay, now we'll have to introduce the notion of a mechanism. What does a mechanism do? A mechanism solicits bids, and based on the bids, it determines an outcome. So what we'll also have as bi, this is the set of possible bids for player I, and b will just the Cartesian product of all of these. This is then the set of bid profiles. And a mechanism now consists of two things. The first thing that we'll have is the function f, which we call outcome rule, which maps from the set of bid profiles to the set of outcomes. So it just takes one of the bid profiles and maps it to an outcome. And then we'll also have a payment rule, which also takes as input a bid profile and maps it to a vector of not necessarily non-negative reals. So payments might also be negative in general. Good. So you could now, and I'm leaving this as an exercise, write down very explicitly what will the outcome and the payment rule be for a first or a second price auction. Interestingly enough, the outcome rule will always be the same, because we were always giving the item to the bidder with the highest value. They differ only in terms of the payment rule. Generally, how does this now go forward? We now say, okay, player I has what as his or her utility. This will be UI, maybe superscript M. We'll often drop the superscript of B, comma VI as VI of F of B minus PI of B. What is this? So we are now taking F of B. This is the outcome under bid profile V. And then, of course, we are asking what is player I's value for this. And then what we also have here, this is just the payment of bidder I under bid profile B. And this is exactly what we saw earlier. F, this is determining who wins the item in the case of a single item, and PI of B now says how much does player I have to pay. So far we were saying the losers don't pay anything, only the winner pays something, but you could also do this in a different way. If you now insist, everybody could pay something. That's just up to you to design this. Importantly enough, what the mechanism sees, this is only the B, and it is not the V. The V, this is only determining the utility of the player, but it is private. Only the player knows the VI. This way of defining utilities is called quasi-linear utilities. Now, what are these bids actually? So far they are just something, but in our examples they were not just something arbitrary, they were exactly possible values. So via the bids, the players were reporting that they have a certain value. That's at least how we interpreted them. And this is also something that you can do much more generally. You can say, okay, maybe bids are just possible valuation functions. And these kinds of mechanisms are called direct mechanisms. So in a direct mechanism, we'll have BI equal to VI, where VI is the set of all possible valuation functions for player I. And this is exactly what we saw in the case of a single item auction. in the case of a single item auction, we set the VI equal to BI equal to, yes, and at this point my notation is a little sloppy because I'm saying, okay, those are actually the real numbers. Why that? Because let's just identify these functions with the values for the item. This is something that was already a little implicit in what I was saying so far. And now at this point we can also interpret this a little more generally. What we were doing there, both the first and the second price auction they both choose an outcome so as to maximize the sum of the BI of X. So what we're saying here is that, and this is something that you can also do whenever you have a direct mechanism, so the players are reporting some valuation functions, and now, okay, let's just take an outcome that maximizes the declared welfare, because something we could also always do is just maximize the sum of what the players are reporting and their value for that outcome will be. This is a kind of mechanism. It's not yet a mechanism, because what is missing to a mechanism, for mechanism, we're still missing the payment rule. And we'll define this actually very soon also for exactly this way of choosing the outcome. But the general dilemma is now, okay, we as the mechanism only see these BI. So if we now wanted to maximize the sum of the valuations, for example, then all we could do is actually maximize the sum of the declared valuations, because we don't know the actual valuations. But what we hope now to do is, by setting the outcome and the payment rule appropriately, the bidders will just tell us their true valuations, and then whenever we're maximizing this thing, then we're at the same time maximizing the sum of the VI of X, because they are telling us the truth anyway. But that's something we definitely have to talk about. Before that, let's maybe see some other examples of what we could now fit into this framework. We might consider, for example, a combinatorial auction. What is a combinatorial auction? We now have a set of items and what is now a little irritating at this point is that this set of items is also usually called capital M, which we also used for the mechanism. So let me still do this here, although this is maybe not a super smart notation. And now each bidder I has a valuation function, which is of course still private because they are still private. They are always private. And this function is mapping from the power set of the set of items to non-negative reals. And the outcomes are feasible allocations of the items. Which we'll write formally as all partitions such that each SI is a subset of M, and SI intersect SI prime will be the empty set. So they are disjoint, meaning that each item is allocated at most once, or each item may be allocated exactly once, depending on how you want to do this. You might want to insist on each item being allocated only exactly once, or at most once. Good. Here you may now also see, okay, this is first of all, this is a generalization of the single item auction, because there this M would be just 1. For this setting, we will be considering different kinds of mechanisms. There are both direct and indirect mechanisms. A direct mechanism would now report this entire function, whereas an indirect mechanism might be just selling each item individually. This is something we'll come to later. Let's see another example. Which is a sponsored search auction. What is this referring to? I hope you remember, this was one of my introductory examples, that whenever you make a search query in one of your favorite search engines, then you're presented, apart from the actual search results, you're presented multiple ads. And these ads are sold in an auction. And how can one capture this? We'll have now K positions. So these might be my search results here. We now have K positions. And we'll have a click-through rate for each position. Which we call alpha j. We assume that the click-through rate at the top position is at least as high as the click-through rate as the next position, and so on until the kth position. And also this is still at least 0, although I should be more explicit. We usually assume that they are even all strictly bigger than than the next one. So we might have here for the first position, we might have some click-through rate. For the second position, we might have again some click-through rate, and so on. And what are now feasible allocations? Feasible outcomes those are the set of vectors x from the set of 0, alpha k up to alpha 1, where each alpha j appears exactly once in X. So this is something you could also interpret as a combinatorial auction, because this would be one item, this would be another item. You can allocate each item at most once, or exactly once. We now do this in a slightly different way, because now those are not just these numbers, but we take them to the n. So we have a vector of click-through rates. Each of the players is getting a click-through rate by getting one of the positions. And we now do this maybe, again, a little complicated way, but this turns out to be helpful next time, because we now say the xi now represents exactly the click-through rate. And this way we can then say, okay, my value for x is equal to vi times xi again, because xi will be exactly my click-through rate. And this is true for some vi that is non-negative. In the lecture notes, you'll find one further example of such a mechanism design problem, which I'll not go through now, but where you'll see, okay, based on all this notation that we have so far, you could also capture a minimization problem rather than a maximization problem. But what we'll do next is we'll discuss what could be a good property that a mechanism fulfills. We've already seen this kind of before in the example of a second price auction. This just felt perfect as a mechanism. And let's now formalize this more generally, what we mean by a perfect mechanism. What is a good mechanism? We've seen that we were kind of happy with the second price auction, because there it was quite easy to participate in, because you just bid your true value, and that's always a good idea. But there are other mechanisms like this which we wouldn't consider good. For example, if we were always giving the item to the youngest bidder, that wouldn't quite make us happy. Why that? Because somehow we wanted to also maximize something which we'll call social welfare in a second. So apart from bidders always wanting to bid their true value, by the way, if we always gave the item to the bidder with these to the youngest bidder, and ignored the bids altogether, you would also want to bid your true value, because this is certainly no worse than any other bid. So there's more to this story. But let's now go through all the properties that we want one by one. The first property that we want is actually that you want to bid your true value, and this is called dominant strategy incentive compatibility. We say that a direct mechanism, what was a direct mechanism? This is one where you can bid your true value. Again, this is a pair of an outcome rule and a payment rule. And we say that this is dominant strategy incentive compatible which we call dsig or just truthful if for every I bidding bi equal to vi is a weakly dominant strategy. That is, for all players, any valuation function and whatever bids we're facing, ui of vi, b minus I, vi is at least ui of bi, b minus I, vi. Let's once again understand this inequality. You are player I. Your value is vi. Everybody is bidding something, so we are facing this bid profile B. Now, you are certainly no worse off if you now unilaterally move to vi. This will give you a utility that is at least as good as what you were bidding before. This in particular means that truthful bidding is a pure Nash equilibrium, because in particular, if everybody else is bidding v minus I, then it is a best response to also bid vi. But this is stronger than this, because even if others are doing something completely crazy, you still want to bid the true value. And as we've seen, the second price auction fulfills this property, and there are also many other mechanisms which fulfill this property. Why do we like this property? For one particular reason, because then we are, as the mechanism, we don't know these VI. All that we are observing is actually the B's. But if now players have an incentive to actually bid their true value, we can just assume that they are bidding their true value, so we can optimize some objective function. And this is something that was already implicit in the second price auction, because what is happening in the second price auction? Who is actually winning the item if everybody's bidding truthfully? The one with the highest value. And let's now see all of this together. So what are the good properties of our second price auction? The second price auction fulfills what? Firstly, strong incentive guarantees. It is dominant strategy incentive compatible. But it also fulfills strong performance guarantees. At our equilibrium, the social welfare which is the sum of the vi of x, is maximized. And thirdly, it is computationally efficient because it runs in polynomial time. This third point might sound trivial right now because, okay, there's only one item, so this is, of course, not super complicated. N bitters still, so you might now discuss how would you implement this most efficiently. Probably you can even do this in linear time, so that's fantastic. But for other problems, like for example for combinatorial auctions, where you have multiple items, suddenly this computational efficiency turns out to be not as trivial. And indeed, this is somehow the point that computer science brought to this entire discussion, because back in the 70s, 80s, economists were saying, okay, we want to have incentive guarantees, and then we want to maximize social welfare, for example. And then they said, okay, this is all fulfilled by some kind of a mechanism that we'll get to know. So they said, okay, we're all set. But then computer science came along and realized, okay, this doesn't even run in polynomial time. And once you insist on polynomial running time, things are getting much more complicated. And this is something that we will be seeing throughout the following lectures. What can you still do if you also insist on polynomial running time? Although, first of all, we'll just talk only about the first two properties, and as it turns out, this third property will maybe at some point then also play a role, and we will realize, okay, we actually cannot do this in polynomial time, and if we start approximating things, then suddenly these other things fail. So this is what's coming up in the following lectures. I hope you're excited about this as I am, and let's see each other soon again. Until then, stay safe. Bye.